Okay, here is a practice test on buffers and solubility. This is Dr. B, and this is a test that I give my students. Oftentimes I reveal what the questions are in advance, which doesn't help as much as you might imagine because you give every student a different solution of acid or base and a different salt where they will determine the solubility. Let's go ahead and show some solved problems. In this particular case, the student is given 100 milliliters of a solution that contains 1.00 grams of acetic acid. It also contains 1.00 grams of sodium acetate, where the Ka, the dissociation constant for acetic acid, is 1.8 times 10 to the minus fifth. You should recognize this as a buffer system where this is your weak acid, this is the conjugate base, and let's determine the pH. This is fairly close to direct plug into the Henderson-Hasselbalch equation. And we're going to need some molarities, and we might as well get moles too since we're asking a serious number of questions here. And the moles of acetic acid is 1/60th of a mole. The moles of sodium acetate is 1/82nd of a mole because it's a little bit bigger. And since we're dealing with 0.1 liters, the molarity, that's moles per liter, increases by a factor of 10. There's the Henderson-Hasselbalch equation. The pKa is the negative log of the Ka, so we take the negative log of that number and we get 4.74. We add to that the log of the concentration of the conjugate base, which is the acetate, which is, we're just going to use molarities here, this number, 0.121 moles per liter. And for the acetic acid, it's 0.167 moles per liter. Do note that you could use moles or molarity, you'd get the same number since the ratios are the same in either case. This stuff has a pH of 4.60. Let's find its pOH. Well, they add up to 14, so it's 9.40. What's the H3O plus concentration? 10 to the minus pH, we'll get that for you. And it's 2.5 times 10 to the minus fifth molar. These multiply through to be 10 to the minus 14th pH, H plus times the OH minus. We'll be using H plus and H3O plus interchangeably. Or you could do 10 to the minus pOH, which is what was done here. And either way you'd get the same answer. It's 4 times 10 to the minus 10th molar. Question number 5. Let's bring up the pH by 1 unit. How could we do that? Well, to bring it up, we better add some base. The base that's present is the acetate right there. So, let's plug into the Henderson-Hasselbalch equation, leaving only the concentration of the acetate as the unknown. There's our pKa for acetic acid. This is the concentration of the acetic acid that we determined before. How much acetate do we use? Well, we have to solve this log-based problem. So we subtract 4.74 from both sides. And then why don't we take 10 to this power, and that'll eliminate the log on that side, since that's what it is. 10 to the 0.86, I think, is about 7.7. We can now cross-multiply but solve for x. And we find that we need a 1.21 molar solution of sodium acetate. Well, why don't we convert that to grams and add it to the 1 gram that we already have? It's 82.03 grams per mole. We have 1/10 of a liter, so we're going to need 9.917 grams in total of sodium acetate. I already have a gram. Add 8.92 grams, and we are good to go. How about lowering the pH by 1 unit? Not a problem. In this case, we need to add acetic acid. So once again, it's exactly the same, only your unknown now is on the bottom. We figured out from an earlier question that the concentration of acetate is 0.121 moles per liter. And so we now will be down to 3.60 from the original 4.60. We subtract 4.74, which is a negative number. Don't let that disturb you. So 10 to the minus 1.14 will be a positive number, albeit a pretty low one, is going to equal 0.121 over x. We cross-multiply now. We find that we need a 1.68 molar solution of acetic acid. Let's turn it into grams and once again tack it on to the 1 gram we already have in solution. checks in at 60 grams per mole, and for our 1 liter solution we find that we need 10.08 grams total. That's a typo. This should be acetic acid, HC2H3O2. So we need an additional 9.0 grams of acetic acid, not the acetate. Sorry about the typo. Oh, that's good right there. And that's how much you need to add to render that solution into a pH 3.6 buffer. Now, this will marginally increase the volume of the solution, which probably renders it a little bit inaccurate, but it should be good enough to go. Question number 7. If 10 mils of 1 molar HCl was added to this original buffer, what will the pH be? Well, we better do the stoichiometry out, because if this is excess, it'll just dominate the pH and it'll go flying down to like 1 or less. But if we still have excess buffer, then the solution should remain buffered and it won't change by too much. The HCl will react with the only base that's present, which is sodium acetate, the conjugate base of acetic acid. So it reacts like in an acid-base manner, or if you will, just like a double replacement. You get HC2H3O2, by night known as acetic acid, along with sodium chloride, a neutral salt. And let's see what we had initially. Well, they said we want to add some HCl. Let's go with moles. So it's 0.01 liters. That's what 100 mils is. Uh-oh, it's not. It's 0.1 liters, right? Nope. Here we are. 10 mils of 1 molar HCl. I was looking up here. 10 mils is 0.01 liters, so we're good to go. It's 0.01 moles. So we have 0.01 moles of hydrochloric acid. Initially, we had 0.0121 moles of sodium acetate. That's 1 gram, where 82 grams is a mole, 1/82nd of a mole. We also had 1/60th of a mole, or 0.0167 moles of acetic acid, because we have a buffer. And we don't really care about the sodium chloride. All of that will react. Notice it is not in excess. So that'll remove almost all the sodium acetate, and it will add 0.01 moles to the acetic acid. Doing our accounting, we see we're out of HCl. We've still got a little bit of sodium acetate, and we have a lot more of the acetic acid. It's now direct plug into the Henderson-Hasselbalch equation. It might worry you somewhat that we're dealing with moles rather than moles per liter, so technically those brackets aren't accurate. But think about it. This would be divided by I guess, maybe is it 0.11? 0.11 liters divided by 0.11 liters. It won't change anything. So we find that the pH went down to 3.63. I'm happy with that. Maybe a little more than I would have expected, but the pH did go down when we added some HCl, but not too much. Let's do the same thing, question number 8, for making it go up. Nope, by adding base. Yes, that will make the pH go up. It's 0.01 moles, just like it was before, but this time this will react with the acid, which is the acetic acid. Doing the double replacement reaction, we see this will make sodium acetate and water. Let's set up a nice table. Initially, we had our 0.01 moles of sodium hydroxide. We had 0.0167, 1/60th of a mole of acetic acid, and 1/82nd of a mole of the sodium acetate there to begin with. That'll all react, giving us not much acetic acid left over, and it will increase the sodium acetate by the 0.01 moles. We find we have a small amount of acetic acid, a pretty large amount of the sodium acetate, and the Henderson-Hasselbalch equation, as we did before, shows us that the pH went up from 4.6 to 5.26, about what we would expect. Part 2 is about solubility. In this case, the student is given 100 mils of an aqueous mixture. We have to use the word mixture because it might not be a homogeneous mixture. If it was, we could call it a solution, but we're just going to call it an aqueous mixture, and it happens to have a gram of calcium carbonate in it, which has lousy solubility. Look at how low the KSP is. Let's determine that molar solubility. Well, I think it'll be the square root, because we have a simple S times S situation that KSP is derived from. So we take the square root of the KSP, and it gives us the solubility of calcium carbonate, which is very low, 10 to the minus fifth moles per liter. But how about grams per liter? Well, we just have to turn moles into grams, and 100 grams is a mole. So now we're up to 10 to the minus 3 grams per liter, 0.00580. And if we wanted to know what the percent is, well, we have to figure out what's the dissolved and the undissolved. It's that many grams per liter dissolved, and we have 1/10 of a liter. So that'll bring it down by a factor of 10. We'll only have that much dissolved, and oh my God, we started with 1 gram, right? So most of it, this says 0.1 grams of calcium carbonate. Oh yeah, once again, let's see, you're given it is 1 gram, so we should have 1 minus this. I'm pretty sure this is a minor error. So this would be 0.99. I think it's going to be, let's see, 1 gram. It would be 0.058% soluble rather than 0.1. And finally, is the solution saturated or unsaturated or supersaturated? Well, most of it didn't go in, so that renders it a saturated solution above it. And you would have your very little that dissolved, your 0.00058 grams, and the rest. Hey, look at that. Now it says 0.1 grams. I think I'm going to change this to 0.1 grams just to render this correct. Now that should do just fine. And there it is, 0.1 grams. And now these numbers should be right. We have the 0.00058 grams that dissolved, almost nothing, and the rest of it, 0.09, almost our full 0.1 grams, is still undissolved as a white powder on the bottom. So we have here a saturated solution. This is a practice buffers and solubility test.